Hello, and welcome to Sleepy Engineering. In this video, we will explore the world of structural steel grades. You will hear about classifications, numbers, standards, and the slow evolution of how steel is defined and categorized in engineering. This narration is intentionally slow, calm, and highly detailed. It is designed to help you relax, to help you unwind, or perhaps to help you fall asleep. There will be no sudden sounds. There will be no music. There will be no strong emotions. Only facts. Only structure. Only the steady voice of information. Now, please sit back. Close your eyes if you wish, and let the story of structural steel grades begin. Structural steel is one of the most important materials used in modern engineering and construction. It is valued for its strength, durability, and ability to be formed into a wide range of shapes and sizes. Engineers rely on structural steel to support loads, withstand environmental forces, and provide a stable framework for buildings, bridges, towers, and many other structures. Structural steel is typically made from iron with a small percentage of carbon and other alloying elements. The carbon content increases the strength of the steel, while allowing it to retain enough ductility to avoid brittleness. Other elements such as manganese, sulfur, phosphorus, and silicon are often included in controlled amounts to improve specific properties of the material. These properties are tested and measured using standardized methods to ensure consistent performance. The use of structural steel dates back to the Industrial Revolution, when new processes such as the Bessemer converter allowed for the mass production of steel at a lower cost. Since then, structural steel has become the backbone of large-scale construction. It is now used in nearly every country around the world, and the systems for grading and classifying it have become increasingly complex and precise. Engineers must consider various factors when choosing a steel grade for a specific application. These factors include yield strength, ultimate tensile strength, elongation, impact resistance, weldability, and corrosion resistance. These properties determine how the steel will perform under load, how it will behave during fabrication and welding, and how it will endure in different environmental conditions over time. The classification of structural steel is handled by national and international standards organizations. These organizations define the specific criteria that a steel product must meet in order to be classified within a certain grade. For example, the American Society for Testing and Materials, or ASTM, provides detailed standards that include chemical composition ranges, mechanical property requirements, and manufacturing tolerances. In Europe, structural steel is typically classified under EN standards, which are developed and maintained by the European Committee for Standardization. These standards are often harmonized across multiple countries to support international trade and collaboration in engineering projects. Japan and other countries also have their own standards, such as the Japanese Industrial Standards, or JIS. While the fundamental principles behind structural steel remain the same across these regions, the exact classifications and naming conventions can differ significantly. This makes it essential for engineers working on international projects to understand how to convert or compare grades between systems. In addition to mechanical performance, the selection of structural steel also depends on how it will be used in the field. For example, steel used in bridge construction may need to resist corrosion from de-icing salts, while steel used in seismic zones must be able to deform without fracturing. Therefore, steel grades often include suffixes or additional designations that indicate special properties such as enhanced toughness or weather resistance. The manufacturing process of structural steel also affects its properties. Hot rolling, cold rolling, quenching, tempering, and other treatments can influence the grain structure of the metal. This in turn affects the way the steel will perform under different types of stress. For this reason, steel grades often include references to how the steel was processed and whether certain treatments were applied. Understanding structural steel grades is not only a matter of selecting the right material. It also involves ensuring compliance with building codes, safety regulations, and quality assurance procedures. Engineers, architects, fabricators, and inspectors all rely on a shared understanding of steel grades to ensure that structures are safe, reliable, and built to last. Errors in grade selection or misinterpretation of specifications can lead to costly delays, structural weaknesses, or even failures. This is why documentation, traceability, and certification are such critical parts of the steel supply chain. Steel mills must provide test reports and certifications that confirm each batch of steel meets the required standards. These documents are reviewed and verified by engineers and inspectors before the steel is used in construction. In some industries, such as nuclear or aerospace, the standards for traceability are even more stringent, requiring a complete history of the material from its origin to its final use. The study of structural steel and its classification is a fundamental part of engineering education. Students learn to read and interpret steel standards, perform mechanical tests, and understand the behavior of steel under different loading conditions. This knowledge forms the basis for more advanced topics such as structural analysis, design optimization, and failure investigation. In recent years, sustainability has also become an important consideration in steel selection. Structural steel is highly recyclable and can be reused in new structures with minimal loss of quality. Some standards now include environmental performance indicators such as carbon footprint or energy usage in manufacturing. These considerations help engineers make informed decisions that balance structural performance with environmental responsibility. As the world continues to develop taller buildings, longer bridges, and more resilient infrastructure, structural steel will remain a central component of modern engineering. Understanding how it is classified and applied is essential for anyone involved in the design, construction, or maintenance of the built environment. In the next section, we will take a closer look at the history of how steel grading systems developed and how they evolved to meet the growing demands of the construction and manufacturing industries. The development of steel grading systems is closely tied to the evolution of industrial manufacturing and the increasing need for reliable and standardized materials in engineering and construction. In the early stages of steel production, there was little to no consistency in the properties of steel being produced, and much of the material used for construction and manufacturing varied greatly in composition, strength, and quality. During the 18th and early 19th centuries, steel was still a relatively expensive and specialized material, often produced in small batches, using labor-intensive methods that lacked precise control over chemical composition. This lack of control meant that each batch of steel could behave differently under load, during fabrication, or over time, making it difficult for engineers and builders to predict performance or ensure safety. As the Industrial Revolution gained momentum and large-scale projects such as railways, bridges, and factories became more common, the demand for consistent and reliable steel grew rapidly. The invention of the Bessemer process in the mid-19th century marked a turning point by allowing steel to be produced on a much larger scale and with improved uniformity. This new capability made it feasible to begin thinking about steel in terms of categories and grades, each with specific mechanical and chemical properties. During this time, early efforts at classification were often informal and localized, based on the experience of individual foundries or engineering firms. Engineers would specify steel according to its visible characteristics or intended use, rather than its measurable properties. However, as engineering projects became more ambitious, and as failures due to material inconsistencies became more serious, the need for formal grading systems became undeniable. The emergence of national and international standards organizations in the late 19th and early 20th centuries laid the foundation for the steel grading systems we use today. Organizations such as the American Society for Testing and Materials, the British Standards Institution, and the German Institute for Standardization began to develop guidelines for defining the properties of steel in a systematic and reproducible way. These standards included methods for testing tensile strength, yield strength, elongation, hardness, and chemical composition, allowing engineers to compare different steels and select the appropriate grade for each application. The idea behind a grading system is to create a framework in which each grade of steel corresponds to a known set of properties, manufacturing tolerances, and suitable applications. Over time, different regions developed their own grading conventions based on local practices, industrial needs, and regulatory environments. For example, the United States adopted the ASTM system, which uses a combination of letters and numbers to indicate the category of material and its intended use. In Europe, the EN standards developed under the European Committee for Standardization became the dominant classification system, often using numerical codes to identify specific grades. Japan and other countries followed similar paths, creating their own systems, such as JS, to reflect regional practices and priorities. These national systems gradually expanded to cover not only mechanical performance, but also aspects such as corrosion resistance, weldability, toughness, and resistance to specific environmental conditions. As global trade and multinational engineering projects increased in the late 20th century, the differences between grading systems began to present challenges. A structural steel specified under one system might not have a direct equivalent in another, leading to confusion, delays, or even design errors. Engineers and fabricators working on international projects often had to convert between grading systems or perform additional tests to verify compatibility. In response to these issues, efforts were made to harmonize and cross-reference different standards. Technical publications, comparison charts, and international agreements helped create a more unified understanding of steel grades. In many cases, engineers now use dual designations or reference equivalent standards to ensure clarity and compliance across borders. The evolution of steel grading systems also reflects advances in testing technology and material science. As our understanding of steel behavior under various loads, temperatures, and environmental conditions has improved, grading systems have incorporated more precise requirements and performance benchmarks. Modern steel grades often include not just tensile strength and chemical composition, but also impact energy absorption at specific temperatures, crack resistance, and fatigue behavior. In addition, manufacturing advances such as thermomechanical processing, microalloying, and controlled rolling have made it possible to tailor steel properties with great precision. These capabilities have led to the creation of specialized grades for demanding applications such as offshore platforms, skyscrapers, pipelines, and earthquake-resistant structures. Steel grading systems have had to evolve in parallel to describe these new materials and their performance criteria accurately. Another significant aspect of the evolution of steel grading systems is the growing emphasis on traceability and certification. Modern steel products are typically accompanied by material test reports that document the exact composition and mechanical properties of each batch. These documents are part of the quality assurance process and are essential for meeting legal and contractual requirements. Certification bodies and inspection agencies play a key role in verifying that the steel complies with the relevant standards and that the grading has been applied correctly. Today, engineers must be familiar with a wide range of grading systems and must understand how to interpret the information provided in standards and certifications. This includes being able to assess whether a particular grade meets the design requirements of a project, whether it is suitable for welding or forming, and whether it has been processed in a way that ensures long-term performance. The evolution of steel grading systems has turned what was once a vague and inconsistent practice into a highly detailed and standardized framework that underpins modern engineering. As we continue into the future, with increasing demands for safety, sustainability, and performance, these systems will continue to grow and adapt. New materials, new processes, and new challenges will require new grades and new standards, but the core idea will remain the same: to provide engineers with a reliable basis for selecting the right steel for every application. The mechanical properties of structural steel are the foundation upon which all grading systems are built. These properties describe how the material responds to forces and stresses, making them essential for ensuring that steel can perform reliably in its intended application. One of the most fundamental mechanical properties of steel is its yield strength. Yield strength is the amount of stress at which a material begins to deform permanently. Below this point, the material will return to its original shape when the load is removed. Beyond this point, however, deformation becomes irreversible. Engineers rely on the yield strength to determine the maximum safe load a structural component can handle without experiencing permanent damage. A higher yield strength typically means the material is stronger, but it may also be less ductile, which means it might not absorb as much energy before fracturing. Another key property is tensile strength, also known as ultimate tensile strength. This is the maximum stress that a material can withstand while being stretched or pulled before breaking. While yield strength tells us when permanent deformation begins, tensile strength tells us the absolute limit before the material fails entirely. The difference between these two values can give insights into the ductility and toughness of the steel. For structural applications, both values are important, but yield strength is often more critical in design calculations because it represents the point where structural integrity begins to degrade. Elongation is another important mechanical property that describes how much a steel sample can stretch before breaking. It is usually expressed as a percentage of the original length of the test specimen. A higher elongation value indicates a more ductile material, which can be beneficial in applications where the steel must absorb energy or undergo deformation without fracturing. Ductility also plays a significant role in the steel's ability to be shaped, bent, or rolled during fabrication processes. Toughness is the ability of steel to absorb energy and resist fracture under sudden impacts or shocks. This property is especially important in applications where the material may be exposed to dynamic or unexpected loads, such as earthquakes, blasts, or heavy machinery. Toughness is typically measured through impact tests, such as the Charpy V-notch test, which determine how much energy a material can absorb before failing. A steel grade with high toughness can prevent catastrophic failures in critical structures. Hardness refers to the material's resistance to indentation, scratching, or wear. Although hardness is not always the most important factor in structural applications, it becomes relevant in components subject to abrasion or surface contact. In many cases, there is a trade-off between hardness and toughness, meaning that harder materials may be more brittle. Engineers must balance these properties based on the specific demands of the project. Fatigue strength is the material's ability to withstand repeated loading and unloading over time without cracking or failing. Many structural components experience cyclic stresses from traffic, wind, machinery, or other sources. Over time, even low levels of cyclic stress can lead to fatigue failure if the material is not properly designed or selected. Steel grades used in bridges, aircraft, and rotating equipment must have sufficient fatigue resistance to ensure long-term durability. Another related property is creep resistance, which is the ability of a material to resist slow, permanent deformation under constant stress at elevated temperatures. Although this is more relevant in high-temperature applications, such as power plants or engines, it is still a factor in the classification of certain steel grades. Modulus of elasticity, often referred to as Young's modulus, measures the stiffness of a material. It defines how much a material will deform elastically under a given load. For steel, the modulus of elasticity is relatively constant across grades and is a crucial factor in structural analysis and design calculations. A stiffer material will deform less under the same load, which can be beneficial in applications where rigidity is required. Poisson's ratio is another elastic property that describes the ratio of lateral strain to axial strain when the material is stretched. Although not as commonly referenced as yield or tensile strength, it plays a role in complex structural analyses where multidirectional stresses occur. Shear strength is the ability of the steel to resist forces that try to cause the internal layers of the material to slide against each other. This is particularly important in connections such as bolts, welds, or rivets, where the load may not be purely axial, but rather applied at an angle. Engineers must calculate shear forces carefully to avoid joint failure. These mechanical properties are not only theoretical values, but are determined through standardized testing procedures in controlled laboratory environments. Tensile tests involve pulling a sample of steel until it breaks, while impact tests measure the energy absorbed during fracture. These tests provide consistent data that are used to classify and grade the steel. The results are usually reported in mill test certificates, which accompany each batch of structural steel and provide traceability and quality assurance for engineering projects. The composition of the steel, including the amount and type of alloying elements, has a direct impact on its mechanical properties. Carbon increases strength but reduces ductility. Manganese improves hardenability and toughness. Chromium and nickel enhance corrosion resistance and strength at high temperatures. These chemical adjustments allow steel producers to tailor the properties of a given grade to meet the specific requirements of various applications. Heat. Treatment processes, such as quenching, tempering, annealing, and normalizing, also play a significant role in modifying the mechanical behavior of steel. Quenching followed by tempering can increase hardness and strength while maintaining acceptable levels of toughness. Annealing reduces internal stresses and increases ductility. Normalizing refines the grain structure and balances strength and ductility. These processes must be precisely controlled to achieve the desired material characteristics. Weldability is another practical mechanical property that affects steel selection. Some steel grades are more prone to cracking or warping during welding due to their composition or hardness. To address this, engineers must consider preheating, post-weld heat treatment, and proper filler materials. Poor weldability can compromise structural integrity and increase construction time and cost. Finally, steel must meet certain safety and performance codes, in addition to having the right mechanical properties. Building codes, bridge design standards, and seismic regulations all specify minimum material requirements for different applications. These requirements are based on decades of research, testing, and real-world experience, and help ensure that the chosen steel grade performs as expected in its service environment. Understanding mechanical properties is essential for selecting the right steel for a project. It enables engineers to predict how a material will behave under load, during fabrication, and over the life of the structure. The precise combination of strength, ductility, toughness, and other properties defines the suitability of a steel grade and supports the safe and efficient design of engineering systems. In the next section, we will explore the chemical composition and alloying elements that influence these properties, and further refine the classification of structural steel grades. The chemical composition of structural steel plays a central role in determining its mechanical behavior, physical properties, corrosion resistance, and suitability for various engineering applications. At its core, steel is an alloy primarily composed of iron with a small percentage of carbon. However, the addition of various alloying elements in specific amounts allows manufacturers to modify and enhance its performance characteristics to meet the requirements of different structural environments. Carbon is the most influential element in steel and is typically present in concentrations ranging from approximately 0.1 to 0.25% in most structural steel grades. As the carbon content increases, so does the hardness and tensile strength of the steel. However, a higher carbon content also reduces ductility and weldability, which may limit the usefulness of high carbon steels in applications that require bending, shaping, or welding. Therefore, structural steel usually contains only a moderate amount of carbon to balance strength and workability. In addition to carbon, manganese is another key element that serves several purposes. Manganese enhances the steel's hardenability and tensile strength, while improving resistance to impact and wear. It also acts as a deoxidizer during the steelmaking process, helping to remove oxygen and sulfur from the molten steel, which contributes to cleaner and more uniform microstructures. Because of its beneficial effects, manganese is almost always present in structural steel, in concentrations typically ranging from 0.5 to 1.6%. Silicon is often added in small amounts as well. Like manganese, it acts as a deoxidizing agent and contributes to strength without significantly decreasing ductility. Silicon also helps refine the grain structure, leading to more uniform mechanical properties. Most structural steels contain between 0.1 and 0.5% silicon. Sulfur and phosphorus are generally considered undesirable impurities in steel. While small amounts are usually unavoidable, excessive concentrations of either element can lead to brittleness, reduced toughness, and lower ductility. For this reason, structural steel grades include strict limits on the maximum allowable sulfur and phosphorus content, typically below 0.05%. Removing these elements requires careful control during the steelmaking process. Some steel grades incorporate additional alloying elements to achieve specialized properties. One common addition is chromium, which improves strength, hardness, and corrosion resistance. Structural steels used in aggressive environments or subject to high temperatures may include small percentages of chromium, especially in weathering steel grades that form protective oxide layers to resist atmospheric corrosion. Nickel is another useful element that enhances toughness, particularly at low temperatures. It also improves corrosion resistance and is often used in combination with chromium in alloy steels designed for harsh service conditions. Vanadium, niobium, and titanium are microalloying elements that are added in very small quantities, often less than 0.1%. These elements help refine the grain structure of the steel, increase strength through precipitation hardening, and improve weldability. Microalloyed steels are valued for their high strength-to-weight ratio and are commonly used in bridges, cranes, and other high-performance structures. Copper can be added to improve atmospheric corrosion resistance, particularly in structural steel grades that are exposed to outdoor environments. Although it is not used in all grades, its inclusion in certain weathering steels helps the material develop a protective oxide layer that slows down further corrosion. Molybdenum contributes to high temperature strength and creep resistance. It is typically used in structural steels that must perform under elevated temperatures for long periods, such as in power plants or industrial furnaces. The inclusion of alloying elements affects not only the mechanical properties, but also the processing characteristics of the steel. For example, higher alloy content may require special procedures during welding, including preheating or post-weld heat treatment. Certain compositions may also affect the steel's response to quenching and tempering, which are heat treatment processes used to improve hardness and strength. Because of these interactions, engineers and metallurgists must understand the full chemical profile of a steel grade before selecting it for a particular application. Standards organizations such as ASTM, EN, and JIS define precise chemical composition limits for each steel grade. These limits ensure that the steel will meet its intended performance specifications and allow for consistent quality across different manufacturers. Steel producers must test each batch of steel to confirm that it meets the required composition and document the results in material test certificates that accompany the product throughout its use. The development of new steel grades often involves adjusting chemical composition to achieve specific performance targets. For example, high-strength low-alloy steels use controlled amounts of microalloying elements to increase strength without significantly increasing weight. These steels are used in applications where reducing material mass is critical, such as in tall buildings or long-span bridges. Advanced high-strength steels used in the automotive industry also rely on carefully tuned compositions to meet both structural and crashworthiness requirements. Sustainability is another factor influencing chemical composition. The recycling of scrap steel is common in structural applications, and the composition of recycled steel must be carefully controlled to prevent the accumulation of undesirable elements. Steelmakers use advanced refining techniques to ensure that recycled material meets the same standards as steel produced from virgin raw materials. In addition to primary alloying elements, trace elements and residuals can also influence the properties of structural steel. Elements such as aluminum, boron, and nitrogen are sometimes intentionally added in small amounts to enhance certain characteristics. Aluminum, for instance, acts as a grain refiner and deoxidizer, while boron can improve hardenability in some steels. However, excessive amounts of trace elements can have negative effects. so their presence must be carefully monitored. The selection of a steel grade, based on chemical composition, must align with the intended application, fabrication methods, environmental conditions, and long-term performance requirements. An engineer designing a structure in a marine environment will choose a grade with enhanced corrosion resistance, while a designer working on a seismic-resistant building may prioritize ductility and toughness. Understanding how each element contributes to the overall behavior of the steel is crucial for making informed decisions. As materials science advances, new compositions and alloying strategies continue to emerge, offering improved performance and efficiency. Nevertheless, the core principles remain the same. The careful control and understanding of chemical composition allow engineers to tailor steel to specific tasks, ensure safety, and optimize the use of resources. In the next section, we will explore how these chemical and mechanical properties are organized into standardized systems, beginning with the American ASTM steel grading system and its role in structural design. The American Society for Testing and Materials, more commonly known as ASTM International, has played a central role in the development of standardized steel grading systems in the United States and across many global markets. Established in the late 19th century, ASTM began as an organization aimed at addressing problems in railroad construction caused by inconsistent materials. Since then, it has grown into a globally recognized body that publishes thousands of technical standards for a wide range of industries, including construction, manufacturing, and transportation. Within the context of structural steel, ASTM standards provide detailed specifications for material composition, mechanical properties, processing methods, and performance criteria. These standards ensure consistency, quality, and safety across a broad array of structural applications. Each steel grade, defined by ASTM, is associated with a unique designation that typically starts with the letter A, followed by a number. The letter A refers to ferrous metals, which include steel and iron. The numerical code identifies the specific standard associated with that material. For example, ASTM A36 is one of the most common structural steel grades in the United States and is widely used in bridges, buildings, and general construction. ASTM A36 steel is a low-carbon steel that offers a good balance of strength, weldability, and machinability. It has a minimum yield strength of 36,000 psi, which gives it its name, and is commonly supplied in shapes such as beams, channels, angles, and plates. While it is not considered a high-strength steel, its versatility and ease of fabrication have made it a popular choice for decades. Another widely used standard is ASTM A992, which is designed specifically for use in wide-flange structural shapes. This steel grade has replaced A36 in many building applications due to its higher yield strength, improved weldability, and tighter tolerances on chemical composition. A992 steel must meet strict criteria for yield and tensile strength, elongation, and carbon equivalent, which influences weldability. ASTM A572 is another example that covers high-strength, low-alloy, structural steel. This grade is available in several yield strength levels, such as 42, 50, 55, 60, and 65 KSI, each offering increasing levels of strength and corresponding reductions in ductility. A572 steel is often used in applications that require weight savings without sacrificing structural capacity, such as long-span bridges or tall buildings. In addition to mechanical and chemical requirements, many ASTM standards include specifications for heat treatment, surface condition, and permissible variations in dimensions. These criteria help ensure that the steel performs predictably during fabrication and in service. For instance, a standard may dictate that plates must be normalized or thermomechanically processed to refine their grain structure and achieve better toughness. ASTM steel specifications are not just limited to structural applications. They also encompass steel for pressure vessels, pipelines, reinforcing bars, and mechanical components. However, the structural steel standards, such as A36, A992, A572, and others, are the ones most frequently encountered in civil engineering and construction. Each standard is developed and maintained by a technical committee made up of engineers, manufacturers, academics, and regulatory officials. These committees review existing standards regularly and update them as necessary to incorporate advances in materials, science, fabrication methods, and safety requirements. The development process is consensus-based and transparent, which helps ensure that the resulting standards are both technically sound and broadly applicable. One important aspect of the ASTM system is that it does not assign a simple strength value to each grade, but rather defines a range of performance characteristics that the steel must meet. This includes not only yield and tensile strength, but also elongation, impact resistance, and chemical composition. By doing so, ASTM standards provide a comprehensive profile of the material's behavior, allowing engineers to select the most appropriate grade based on the demands of the specific project. In practice, engineers specify ASTM grades in design documents, purchase orders, and construction specifications to ensure that all parties involved in a project are working with materials that meet the same expectations. Steel mills must produce the material in accordance with the standard, and third-party testing laboratories verify compliance through mechanical tests and chemical analyses. This system of specification and verification creates a chain of quality control from production to installation. The ASTM grading system also facilitates traceability, which is critical for quality assurance and regulatory compliance. Each batch of steel must be accompanied by a mill test report that certifies the material meets the requirements of the specified standard. These reports include detailed information such as heat number, chemical analysis, mechanical test results, and processing history. If a problem arises in service, engineers can trace the material back to its origin and determine whether it was manufactured according to specification. While ASTM standards are primarily used in the United States, they are also recognized internationally, particularly in countries that trade with the US or follow American engineering practices. In some cases, ASTM grades are used alongside other systems such as ISO, EN, or JIS, especially in multinational projects. To support this interoperability, ASTM publishes equivalency tables and cross-references that help engineers convert between different standards. Another advantage of the ASTM system is its adaptability. New steel grades can be introduced as industry needs evolve, and existing grades can be modified to reflect improved manufacturing techniques or emerging performance requirements. This makes the ASTM system a living framework that evolves with technology while maintaining its foundational principles of consistency, reliability, and safety. The flexibility and comprehensiveness of the ASTM steel grading system have contributed to its widespread acceptance and longevity. Engineers, fabricators, and contractors rely on these standards every day to make informed decisions about material selection, design, and construction. Whether building a high-rise tower, a highway bridge, or a simple warehouse frame, knowing the steel grade and understanding its properties is essential to achieving a successful outcome. In the next section, we will turn our attention to the European EN steel grading system, which offers a different approach to classification and performance definition, reflecting the regional practices and regulatory environment of Europe. The European EN steel grading system is a comprehensive and standardized method for classifying structural steels across the European Union and other countries that adhere to the European norms. Developed by the European Committee for Standardization, also known as CEN. This system provides a uniform approach to steel specification, replacing a variety of national standards that were previously used by individual countries such as Germany, France, and the United Kingdom. At the core of the EN grading system is the EN 1025 series, which defines technical delivery conditions for hot-rolled structural steel. The most commonly used grades within this series are labelled with the prefix S, followed by a number that indicates the minimum yield strength of the steel in megapascals. For example, S235 has a minimum yield strength of 235 MPa, while S355 has a minimum of 355 MPa. These values are measured on standard test specimens and provide a clear indication of the steel's strength classification. The designation is often followed by additional letters and numbers that describe other important characteristics. For instance, letters such as JR, J0, and J2 indicate the steel's impact toughness at different temperatures. JR means the steel has been tested for impact energy at room temperature, J0 at 0 degrees Celsius, and J2 at minus 20 degrees Celsius. These classifications help engineers choose a steel grade that meets both strength and toughness requirements, especially in climates where materials may be exposed to low temperatures and dynamic loads. The EN system also includes suffixes to indicate the method of deoxidation and other material properties. For example, the letter G indicates that the steel is supplied in a normalized or normalized rolled condition, which improves its mechanical properties and microstructure. Similarly, the addition of a Z suffix, such as Z25, denotes that the steel has been tested for through-thickness properties, making it suitable for applications where resistance to lamellar tearing is important, such as in thick welded structures. One of the key advantages of the EN system is its emphasis on technical delivery conditions, which go beyond mere chemical composition and mechanical strength. These conditions define the acceptable ranges for chemical elements, required mechanical tests, permissible dimensional tolerances, and quality control measures. This level of detail provides engineers, fabricators, and purchasers with a high degree of confidence in the performance and consistency of the steel they are using. The EN system is also supported by harmonized European standards that align with the requirements of the Construction Products Regulation. This regulatory framework ensures that structural steels used in construction projects meet safety, environmental, and performance criteria across all EU member states. As a result, materials specified and certified according to EN standards can be used freely within the European Economic Area, facilitating trade and simplifying project coordination. EN grades are used in a wide range of structural applications, including bridges, buildings, towers, offshore structures, and industrial facilities. The flexibility of the system allows engineers to select a grade that matches the specific performance demands of each component, whether those demands involve high strength, low temperature toughness, weldability, or corrosion resistance. In particular, the S355 grade series has become one of the most widely used structural steels in Europe due to its good balance of strength and weldability. Within the S355 family, variants such as S355J2 and S355NL offer additional toughness or low temperature capabilities for critical applications. Another strength of the EN system is its integration with material certification procedures. Structural steels are often delivered with an inspection certificate that complies with EN 1204, a standard that defines the types of inspection documents. For example, a 3.1 certificate indicates that the material has been tested by the manufacturer and that the results are included in the certificate, while a 3.2 certificate includes verification by an independent third party. These documents are critical for ensuring traceability and confirming that the material meets the required specifications. The EN grading system also includes specialized steels for specific environments and applications. For example, the EN 100-255 standard covers structural steels with improved atmospheric corrosion resistance, such as weathering steels that form a stable oxide layer on their surface. These steels are suitable for outdoor structures and bridges where long-term durability and minimal maintenance are desired. Similarly, the EN 100-253 and EN 100-254 standards address normalized and thermomechanically rolled steels, respectively, which offer enhanced mechanical properties and processing benefits. Engineers and designers must also consider welding compatibility when selecting EN steel grades. Most EN structural steels are designed to be weldable, but the specific welding parameters depend on factors such as carbon equivalent, thickness, and joint design. The EN system provides guidance on preheating, interpass temperatures, and post-weld treatments to ensure that welds meet the same performance criteria as the base metal. The widespread adoption of the EN system has helped improve material consistency and simplify design processes across borders. By providing a common language and a set of harmonized standards, it enables multinational engineering firms, fabricators, and contractors to collaborate more efficiently and to specify materials with confidence. Although the EN system differs from the American ASTM system in structure and terminology, it fulfills many of the same functions and often achieves equivalent performance outcomes. In fact, cross-referencing tables exist to help engineers compare EN grades with their ASTM or ISO counterparts when working on international projects. The future of the EN grading system continues to evolve as materials science advances and as new performance requirements emerge. Research into high-performance steels, improved corrosion resistance, and sustainability is ongoing, and future revisions of the standards may reflect these developments. Nevertheless, the foundational principles of clarity, precision, and safety will continue to guide the classification and use of structural steels in Europe. In the next section, we will examine the ISO steel classification system, which aims to provide a unified international approach and further harmonize steel standards across global markets. The ISO steel classification system represents an international effort to unify the various national and regional standards for steel grading under a common framework. The International Organization for Standardization, known as ISO, was established in 1947 to develop and promote globally recognized standards across many industries. In the field of structural steel, ISO provides a set of guidelines and designations intended to simplify international trade, ensure material compatibility, and create consistent expectations for performance and quality. Unlike region-specific systems such as ASTM in the United States or EN in Europe, ISO aims to serve as a neutral global platform. One of the core documents related to steel within the ISO system is ISO 4948, which defines the classification of steels based on chemical composition and intended use. ISO steel grades are generally categorized into two main types: unalloyed steels and alloy steels. Unalloyed steels contain only small amounts of elements other than iron and carbon, and are typically used in applications where strength and workability are the main concerns. Alloy steels include significant additions of elements such as chromium, nickel, or molybdenum to achieve enhanced mechanical or chemical properties. ISO 4948 works in conjunction with ISO 4949, which establishes a coding system for steel names. This alphanumeric coding provides specific information about the steel's chemical composition and intended function. The system is designed to be logical and descriptive, allowing users to understand the material's essential characteristics simply by reading its code. For example, a typical ISO steel code such as 42CRM04 indicates a steel containing approximately 0.42% carbon, with additional alloying elements, chromium and molybdenum. This systematic approach helps eliminate ambiguity and allows engineers to compare different steels across national borders. Another important standard is ISO 630, which focuses specifically on structural steels. ISO 630 defines grades of steel for use in structural applications and includes requirements for mechanical properties such as yield strength, tensile strength, and elongation. It also outlines acceptable ranges for chemical composition and provides guidelines for heat treatment, dimensional tolerances, and testing procedures. ISO 630 is frequently referenced in international construction projects and by countries that do not have extensive national steel standards of their own. One of the strengths of the ISO system is its emphasis on harmonization. Many ISO steel standards are developed in collaboration with other standardization bodies such as CN and ASTM. This cooperation leads to equivalence tables and joint publications that allow engineers to identify comparable materials across systems. For example, a structural steel specified under ISO may have an equivalent designation in EN or ASTM, making it easier for multinational teams to source materials and design components with confidence. The ISO system also supports a wide range of product forms, including plates, bars, sections, and tubes. Specific standards exist for each product type, such as ISO 657 for hot-rolled sections and ISO 4942 for steel tubes. Each of these standards provides detailed criteria for dimensions, tolerances, surface conditions, and performance requirements. This level of detail ensures that products conform to expected levels of quality and can be integrated seamlessly into larger structures or assemblies. ISO also promotes standardization in testing procedures. ISO 6892 specifies the method for tensile testing of metallic materials, while ISO 148 covers impact testing using the CHARPY method. These standardized procedures ensure that test results are comparable regardless of where the material is manufactured or tested. Consistency in testing is critical for verifying compliance with material specifications and for maintaining structural integrity in the final application. One challenge associated with the ISO steel classification system is its relative complexity compared to more familiar regional standards. The coding system, while logical, may be unfamiliar to engineers who are more accustomed to simpler alphanumeric designations used in ASTM or EN standards. Furthermore, ISO standards often reference multiple supporting documents that must be consulted to fully understand a material's specification. Despite these complexities, the advantages of a unified global standard are clear. In an increasingly interconnected world, the ability to specify and source structural steel across borders without confusion or redundancy is essential. ISO standards help manufacturers streamline production, reduce inventory complexity, and enter new markets with materials that are already recognized and accepted. Engineers benefit from a clear and consistent set of expectations for material performance, simplifying the design process and reducing the risk of miscommunication. ISO steel grades are particularly useful in projects that involve international collaboration, such as infrastructure development, financed by multinational organizations, large-scale industrial facilities, or globally sourced supply chains. In these contexts, the ability to specify materials using a neutral, internationally accepted system helps avoid disputes and ensures compatibility across all phases of the project. As the global steel industry continues to evolve, the role of ISO is likely to become even more important. New standards are being developed to address emerging materials, such as advanced high-strength steels, corrosion-resistant alloys, and steels designed for additive manufacturing. These developments reflect the ongoing need for flexibility and innovation in standardization, while still maintaining the principles of clarity, reliability, and interoperability. The ISO system also incorporates sustainability considerations. Environmental standards such as ISO 14001 influence steel production practices, encouraging manufacturers to minimize waste, reduce energy consumption, and lower emissions. As concerns about climate change and resource efficiency grow, the integration of environmental goals into material standards will become increasingly significant. In summary, the ISO steel classification system provides a robust and internationally accepted framework for specifying structural steel. Its focus on chemical composition, mechanical performance, and standardized testing ensures that materials meet consistent criteria, no matter where they are produced. While it may require greater familiarity with documentation and coding, the system's global scope and collaborative development process make it an invaluable tool for modern engineering. In the next section, we will explore the Japanese JIS steel classification system, which offers another perspective shaped by the unique industrial and regulatory environment of Japan. The Japanese Industrial Standards, or JIS steel grading system, is Japan's national framework for classifying and regulating steels used across various industrial sectors, including construction, automotive, shipbuilding, and machinery. Established and maintained by the Japanese Industrial Standards Committee under the Ministry of Economy, Trade and Industry, the JIS system provides a standardized set of naming conventions, material properties, and testing requirements that ensure quality consistency and performance throughout the domestic and international steel supply chain. JIS steel grades are widely respected for their high manufacturing precision, tight tolerances, and rigorous performance expectations, which have made Japanese steel products especially desirable in industries that demand exceptional reliability and strength. The structure of the JIS designation system begins with a prefix consisting of one or more letters which indicate the application or material category, followed by a numerical code that identifies the specific grade or series. For example, the prefix SS refers to structural steel, where SS stands for structural steel, and is followed by a number that denotes its mechanical properties, such as SS400. SS400 is one of the most common and widely used JIS structural steel grades and is roughly equivalent to ASTM A36 or EN-S235. It features a minimum tensile strength of 400 MPa, which gives the grade its name, and is valued for its weldability, machinability, and suitability in general fabrication work. JIS standards are not limited to structural applications, but also include grades for alloy steels, carbon steels, tool steels, stainless steels, and more, with designations like S45C, SUS 304, and SKD11, each representing a different category of steel with tailored properties. S45C, for example, is a medium carbon steel often used in mechanical parts and forging, while SCM 440 is a chromium molybdenum alloy steel used in high-strength applications. SUS 304 is one of the most recognized stainless steel grades worldwide and is known for its corrosion resistance and formability. The JIS system places strong emphasis on chemical composition and mechanical performance, and its standards include precise instructions for how the steel should be manufactured, tested, and delivered. The material's properties, such as yield strength, tensile, strength, elongation, hardness, and toughness, are tightly regulated with detailed guidelines on how samples should be prepared and which testing methods should be used. This creates a high level of uniformity and reliability, making JIS steels suitable for high-performance environments where failure is not an option. An important feature of the JIS system is its connection to the broader industrial landscape of Japan, where meticulous manufacturing processes and a culture of continuous improvement play a significant role. Japanese steel mills adhere strictly to JIS standards and often exceed them by adopting advanced production technologies such as vacuum degassing, continuous casting, and precision rolling. This allows them to produce steels with minimal impurities, consistent grain structures, and superior surface finishes, which in turn enhances the steel's mechanical behavior and weldability. In practice, JIS steel grades are used across nearly every major Japanese industry and are increasingly adopted in global markets due to their high quality and consistent performance. In construction, SS400 and SM490 are frequently used in beams, columns, and frames. In automotive engineering, steels like SPHC and SPCC are utilized in body panels, chassis components, and structural reinforcements. In the realm of toolmaking, SKS and SKD series, steels provide high hardness and wear resistance for dies and cutting tools. Stainless steels such as SUS 304 and SUS 316 appear in everything from kitchen appliances to chemical processing equipment. While the JIS system shares many features with other international standards, it also includes some distinctions that engineers must be aware of when specifying materials for multinational projects. One key difference lies in the way grades are assigned and referenced. Unlike ASTM or EN standards, which often rely on minimum yield strength values or detailed property codes, the JIS naming system focuses more on categorization by use and composition, which can sometimes make direct equivalency challenging. However, equivalency tables are available and widely used in engineering practice to help convert between JIS and other steel standards such as ISO DIN or ASTM. Another feature of the JIS framework is the regular revision of its standards. The JIS committee conducts reviews and updates periodically to reflect new technologies' shifts in industry demand and improvements in metallurgical understanding. This ensures that the system remains current and responsive to the evolving needs of the global market. These updates are published and made available to manufacturers and engineers, enabling them to stay aligned with best practices. JIS standards also integrate requirements for traceability and quality assurance. Steel products delivered under JIS must be accompanied by certificates of compliance and detailed inspection records, including results from mechanical and chemical tests. This documentation ensures accountability throughout the supply chain and provides end users with confidence in the origin and quality of the material. The reputation of Japanese steel as being among the most reliable in the world is in part a result of this meticulous approach to specification and verification. In many ways, the JIS steel grading system reflects the broader values of Japanese engineering, which prioritize precision reliability and long-term performance. It supports innovation while maintaining a foundation of rigorous quality control and standardization. As such, it plays a critical role not only in domestic manufacturing, but also in global industries that rely on Japanese components, technologies, and expertise. In the following section, we will examine the Chinese GB steel grading system, which is increasingly influential as China continues to expand its role as a global leader in steel production and infrastructure development. The Chinese GB steel grading system is the national standard for steel classification in the People's Republic of China and is administered by the Standardization Administration of China, also known as SAC. GB stands for Guobiao, which translates to national standard, and the system is designed to provide a unified and regulated method for naming, testing, and applying steel materials across the vast industrial landscape of China. With China being the largest producer and consumer of steel in the world, the GB steel grading system plays a crucial role in shaping global steel production trends, trade flows, and engineering practices. The GB system includes thousands of standards covering every category of steel, from structural and alloy steels to stainless steels, tool steels, and high-performance materials. Within the GB framework, structural steels are among the most commonly used, and their designations typically begin with the letter Q, which stands for yield point or yield strength. The number that follows indicates the minimum yield strength in megapascals. For example, Q235 is a low-carbon structural steel with a minimum yield strength of 235 MPa and is widely used in construction bridges, pipelines, and general fabrication. Another frequently used grade is Q345, which offers higher strength and is suitable for more demanding structural applications. These steels are further categorized by letters that reflect impact resistance at various temperatures, such as Q345B, Q345C, Q345D, and Q345E, with each successive letter denoting increased toughness at lower temperatures. The GB system also covers alloy steels, using designations that reflect both carbon content and alloying elements. For instance, 20 CCRMO denotes a steel containing approximately 0.20% carbon, with chromium and molybdenum as the main alloying additions. This type of steel is commonly used in the automotive industry for gears, shafts, and other components that require strength, toughness, and wear resistance. Similarly, tool steels are categorized with prefixes such as T for high-speed steels or CR for chromium-based alloys, with codes like T10 or CR12 MOVI used to specify material for cutting tools, molds, and dies. Stainless steels within the GB system use the 0CR prefix followed by numbers indicating the chemical composition. For example, 0CR18Ni9 is a designation for a stainless steel containing 18% chromium and 9% nickel, which is roughly equivalent to the internationally known grade 304. These naming conventions provide a basic yet informative snapshot of the steel's chemical structure, which helps engineers and fabricators select materials appropriate for the environment and mechanical demands of their applications. A distinctive feature of the GB system is its integration with China's broader economic and industrial planning. Many GB standards are linked with national infrastructure initiatives, manufacturing priorities, and quality assurance programs, which means that compliance with these standards is not just a technical matter, but also a regulatory and economic requirement. This integration ensures that materials used in large projects such as railways, airports, bridges, and energy facilities meet rigorous criteria for strength, safety, and durability. Testing and certification within the GB system are highly regulated and involve third-party inspections from approved organizations. Materials must undergo mechanical testing such as tensile strength, elongation, impact, resistance, and hardness, as well as chemical analysis to verify alloy content. In many cases, manufacturers must also adhere to production process standards to ensure consistency across batches and long-term performance. Inspection certificates and material test reports are required to document compliance and are commonly reviewed during construction audits and quality control processes. One of the challenges of the GB system from an international perspective is the limited availability of official English translations and cross-reference tools. While many Chinese steel producers provide documentation in both Chinese and English, the lack of standardized translations can lead to misunderstandings or incorrect material substitution in international projects. However, with China's growing participation in global infrastructure development and trade agreements, there has been increasing effort to harmonize GB standards with international systems, such as ISO ASTM and EN. In fact, many modern GB steel grades have recognized equivalents or close matches in other standard systems, allowing engineers to find suitable substitutes when designing multinational projects. The GB system is also notable for its continual evolution. China frequently updates its standards to reflect technological advances and the changing demands of industry. These updates are managed by technical committees composed of researchers, engineers, industry experts, and government representatives who collaborate to ensure that standards remain current and effective. Recent updates have included improvements in environmental performance guidelines, corrosion resistance, and the development of high-strength and ultra-high-strength steels for automotive and aerospace applications. Another strength of the GB grading system lies in its ability to serve a wide range of industries, from traditional construction and transportation to emerging fields such as renewable energy electronics and high-speed rail. This versatility is supported by a vast network of steel producers and research institutions that contribute to both the development and implementation of standards. As a result, the GB system is not only a classification tool, but also a strategic mechanism that supports China's goals in industrial modernization and global competitiveness. The quality of Chinese steel products has improved dramatically in recent decades, driven by investments in manufacturing equipment, automation, metallurgical science, and quality control systems. Today, many Chinese steel grades meet or exceed international standards and are used in complex and safety-critical applications around the world. The GB grading system has been central to this transformation by providing a rigorous and adaptable framework for production inspection and application. In summary, the GB steel classification system is a vital component of China's industrial ecosystem and plays a growing role on the international stage. Its focus on strength consistency and regulatory alignment makes it an effective tool for ensuring the reliability and performance of structural steel across a broad spectrum of applications. As the system continues to evolve and align with global standards, its influence will likely increase further, solidifying China's position as a global leader in steel production and engineering. In the next section, we will explore the Indian BIS steel grading system and its contributions to both domestic and international engineering standards. The Indian BIS steel grading system is governed by the Bureau of Indian Standards, which serves as the national body responsible for establishing and maintaining technical norms for a wide array of materials and industries, including steel. The BIS system plays a foundational role in India's infrastructure, automotive energy, and manufacturing sectors by providing a structured method to classify and regulate steel products. The steel grades defined by BIS are designed to ensure safety, durability, and performance in a country that is rapidly developing and modernizing its industrial base. One of the most commonly used BIS standards for structural steel is IS 2062, which specifies the requirements for hot-rolled low and medium tensile structural steel. Within IS 2062, grades are indicated by their minimum yield strength in megapascals. For example, grades such as E250, E350, and E450 refer to steels with minimum yield strengths of 250, 350, and 450 MPa, respectively. These designations may be followed by quality designations such as A, B, or C, which reflect different levels of impact toughness, where C offers the highest impact resistance and is suitable for colder climates or dynamic loads. The designation may also include symbols to specify delivery conditions, such as N for normalized steel or AR for AS rolled condition. In this way, the BIS system uses a layered nomenclature to communicate not just strength, but also quality and processing information. The BIS grading framework includes additional standards for other steel categories, such as IS 1786 for high-strength deformed bars used in reinforced concrete structures, IS 4923 for hollow steel sections, and IS 1079 for cold-rolled steel sheets. Each standard includes specific details about chemical composition, permissible tolerances, surface finish, and mechanical properties. These specifications ensure that materials used across different sectors of the economy meet appropriate safety and performance requirements. The BIS system emphasizes national consistency and suitability for local conditions, which is essential in a country with diverse climates and construction practices. One unique feature of the BIS approach is its incorporation of Indian climatic and seismic data into material performance expectations. For example, in regions with high humidity or coastal exposure, corrosion resistance is a critical factor in steel selection. Similarly, in areas prone to earthquakes, steel used in construction must meet enhanced ductility and toughness standards. The BIS system also integrates safety margins into its grading criteria, taking into account variations in material behavior due to transportation handling and fabrication processes. Testing and certification are integral to the BIS system. Steel manufacturers must undergo regular audits, and their materials must be tested in certified laboratories according to defined protocols. Tests typically include tensile strength, elongation, yield, strength, bend tests, and sometimes impact or hardness testing, depending on the application. Products that meet the criteria are allowed to carry the ISI certification mark, which indicates compliance with the relevant BIS standard. This mark is widely recognized and trusted by engineers, builders, and government agencies throughout India. Another important aspect of the BIS system is its relationship with international standards. While BIS develops its own technical norms, it often references or adapts global standards, such as those from ISO ASTM or EN, to suit local needs. This hybrid approach allows Indian engineers to work within a familiar national framework, while still maintaining compatibility with international markets and supply chains. For example, IS 2062, grade E250B, is considered roughly equivalent to ASTM, A36, and EN S235JR, which simplifies the task of material substitution in multinational projects. The evolution of the BIS system is driven by input from technical committees composed of engineers, researchers, industry professionals, and government representatives. These committees conduct regular reviews to update existing standards and develop new ones in response to technological advances and feedback from users. Recent updates have focused on improving the weldability, formability, and corrosion resistance of steel grades, as well as on developing eco-friendly manufacturing practices that align with India's sustainability goals. In addition to mechanical and chemical standards, the BIS framework includes requirements for traceability and documentation. Manufacturers must maintain detailed records of production batches, chemical compositions, and test results, which must be available for inspection. This traceability helps ensure accountability and quality control throughout the steel supply chain. It also supports regulatory oversight and provides valuable data in the event of material failure or structural issues. The BIS system is increasingly important in the context of India's ambitious infrastructure programs, including smart cities, high-speed rail, renewable energy projects, and industrial corridors. These initiatives demand large volumes of high-quality steel with predictable and verifiable properties. The BIS grading framework provides the foundation for meeting these demands by offering clear specifications, reliable testing protocols, and a nationally coordinated approach to material certification. As India expands its presence in the global steel market, the BIS system is expected to play a larger role in international trade. Indian steel products that meet BIS standards are now being exported to a growing number of countries, especially in Asia, Africa, and the Middle East. This trend is supported by the Make in India initiative, which encourages domestic manufacturing excellence and quality improvement. In this context, the BIS grading system serves not just as a domestic regulatory tool, but also as a benchmark for global competitiveness. In summary, the Indian BIS steel grading framework is a robust and evolving system that ensures the safe, reliable, and efficient use of steel across India's diverse and growing economy. Its focus on structural integrity, local relevance, and international compatibility makes it a valuable tool for engineers and manufacturers alike. In the next section, we will examine how to compare and convert between different steel grading systems to ensure compatibility in global engineering projects. In modern engineering, projects often involve the collaboration of manufacturers, suppliers, and engineers from different parts of the world, which means that comparing and converting between various steel grading systems is an essential task for ensuring material compatibility and structural integrity. While each national or regional system, such as ASTM, EN, JIS, GB, and BIS, was developed independently to meet specific local needs, globalization has increased the necessity for engineers to understand how different grades relate to one another and how equivalent materials can be substituted in practice without compromising performance or safety. The process of comparing steel grades involves analyzing mechanical properties such as yield strength, tensile strength, elongation, hardness, and impact resistance, as well as chemical composition, including carbon content and the presence of alloying elements like chromium, nickel, molybdenum, manganese, and vanadium. It also requires attention to production processes, quality standards, heat treatment conditions, and dimensional tolerances, because even if two steels have similar strength values, differences in alloy content or heat treatment can significantly affect weldability, corrosion resistance, and fatigue behavior. Engineers often rely on equivalency tables published by standards organizations, academic research institutions, or material databases that offer cross-reference charts comparing steel grades from different systems. For example, ASTM A36 is often considered equivalent to EN S235JR, JIS SS400, GB Q235, and IS E250. Though slight differences in chemical composition or mechanical values may exist. These charts are helpful for preliminary identification, but engineers must still verify whether the specific steel meets all project requirements, especially when the application involves critical loading conditions, high temperatures, or corrosive environments. Converting between steel grades becomes more complex when high-performance or specialized steels are involved, because properties like toughness at low temperatures, resistance to hydrogen embrittlement, or thermal expansion must be evaluated with precision. For example, stainless steels such as SUS 304 in the JIS system, 1.4301 in EN, and AESE 304 in ASTM share nearly identical chemical structures, but differences in testing standards or surface finish requirements may lead to different results in performance. The task of comparing steels must also consider the context of certification and traceability. Even if two grades are chemically similar, the quality control procedures in place during manufacturing, the type of documentation provided, and the inspection protocols can vary significantly between regions. Projects in aerospace, nuclear, or offshore applications often require that the steel not only matches a certain grade on paper, but also comes from mills that are certified by specific authorities or hold accreditation under recognized quality systems such as ISO 9001 or ASME. In many international projects, engineers use dual certified steels that meet multiple standards simultaneously. These steels are produced to comply with both ASTM and EN specifications, for example, and are labeled accordingly. This approach simplifies procurement and design, but often comes with higher material costs due to the additional processing and testing involved. Dual certification is especially useful when steel components are manufactured in one country and installed or inspected in another, as it reduces the risk of rejection or non-compliance during audits. Another tool engineers use to compare steel grades is simulation or laboratory testing. When in doubt about material equivalency, samples can be subjected to tensile tests, impact tests, chemical analysis, and corrosion tests to determine whether the alternative grade performs adequately under real-world conditions. This empirical method is particularly important in retrofitting or repair work, where original specifications may be outdated or unavailable, and a modern replacement must be validated through direct testing, rather than relying on equivalency tables alone. Documentation also plays a critical role in comparing and converting steel grades. Material Test Certificates, or MTCs, must be carefully reviewed to ensure that they include data relevant to the required standards, including heat number, batch number, test results, and compliance statements. Engineers must check whether the reported data aligns with the target specification and whether any deviations exist that could affect structural or mechanical performance. This is especially true in cases where imported steel is being used in a jurisdiction that mandates local codes or where legal liability depends on strict adherence to standards. In addition, familiarity with international harmonization efforts can aid in comparing steel grades. Organizations such as ISO have been working to unify material standards, and many national bodies have adopted ISO-based norms or integrated ISO references into their grading systems. As a result, modern standards increasingly share common definitions for test procedures, property limits, and dimensional tolerances, which helps engineers make informed decisions when comparing grades. Despite this progress, complete standardization has not yet been achieved, and discrepancies between systems still exist. Engineers must therefore approach conversions with caution and prioritize safety, documentation, and validation over convenience or cost saving. In some cases, engineers may decide not to substitute materials at all if the risks of misalignment or misinterpretation are too high. In summary, comparing and converting between steel grading systems is a complex but necessary process in the globalized engineering environment. It requires not only technical knowledge of steel properties and standard systems, but also attention to detail in documentation, testing, and quality control. equivalency tables, dual certifications, laboratory tests, and harmonization efforts all play a role in making steel grades from different systems functionally interchangeable. But final responsibility always rests with the engineer to ensure that the material chosen meets all structural, safety, and regulatory requirements. In the next and final section, we will conclude our exploration of structural steel grades by reflecting on the importance of standardization and how understanding these systems supports safer, stronger, and more efficient engineering worldwide. The global engineering landscape depends heavily on consistency, predictability, and safety, all of which are directly influenced by how materials such as structural steel are classified and regulated. As we have explored throughout this video, steel grading systems play a fundamental role in connecting design intent with physical reality, allowing engineers to specify, select, and utilize materials with confidence across a wide range of applications, whether in bridges, buildings, ships, pipelines, or machinery. The reliability of a structure is closely tied to the quality and appropriateness of the steel used. And that quality is ensured through standardization. The existence of multiple national and regional grading systems reflects the historical, industrial, and cultural paths taken by countries as they developed their own engineering practices. Systems such as ASTM in the United States, EN in Europe, JS in Japan, GB in China, and BIS in India have each evolved to meet specific needs, climates, industries, and regulatory environments. Yet despite their differences, all of these systems share a common purpose: to define clear and measurable expectations for steel performance. These definitions allow manufacturers to produce steel to exact specifications, enable engineers to design with confidence, and help regulators enforce safety and quality requirements. The importance of standardization becomes even more evident in a globalized world where materials are sourced internationally and construction projects span borders. Without standardization, the risk of using incompatible or substandard materials increases significantly, leading to potential failures, delays, or legal consequences. Engineers must often navigate complex procurement landscapes where steel from different systems must be compared, validated, and certified. This requires not only a technical understanding of material properties, but also fluency in documentation, inspection, and international regulations. Fortunately, many efforts are underway to promote harmonization and interoperability among grading systems. International organizations like ISO have made significant strides in defining universal testing methods and property classifications, while trade agreements and engineering codes increasingly reference equivalent standards from other regions. As these efforts expand, the task of material selection becomes more streamlined, but the responsibility of engineers to interpret and apply these standards correctly remains unchanged. The role of education and professional development is also central to the effective use of steel grading systems. Engineers must be trained to understand the implications of grade selection, including mechanical behavior, weldability, corrosion resistance, and fabrication considerations. They must also know how to interpret test reports, assess quality certifications, and verify compliance with local codes and project requirements. By building this knowledge early and reinforcing it through ongoing learning, the profession ensures that standardization is not just a theoretical concept, but a practical tool for safe and effective engineering. In addition to enabling safety and performance, standardization also contributes to economic efficiency and innovation. By reducing variability and uncertainty, standardized steel grades allow manufacturers to optimize production, minimize waste, and maintain consistent quality across large volumes. Designers can confidently create modular systems, prefabricated components, and interoperable structures that meet strict tolerances and assembly criteria. At the same time, standards provide a framework for developing new materials and technologies. As demands evolve, new grades can be introduced that meet emerging needs in sectors such as renewable energy, high-speed rail, or aerospace, all while remaining compatible with existing classification systems. Looking to the future, the importance of standardization in structural steel will only grow as the complexity of projects increases and the pressure to build faster, safer, and more sustainably intensifies. New challenges, such as climate change, population growth, and urbanization, will require innovative engineering solutions that depend on reliable materials and globally recognized standards. Steel, as one of the most versatile and widely used materials in the world, will continue to play a central role in meeting these challenges, and the systems that define its properties will remain critical to that mission. In summary, steel grading systems are more than just technical catalogues. They are the language through which engineers communicate expectations, manufacturers deliver quality, and society builds the infrastructure that supports modern life. Understanding these systems, knowing how to compare them, and applying them responsibly is a core part of engineering practice. As we conclude this video, we recognize that the world of structural steel is complex, diverse, and deeply interconnected, and that by mastering its standards, we build not only stronger structures, but also a more reliable and cohesive global engineering community. Thank you for listening to this slow and detailed journey through the world of structural steel grades. We hope this information has brought both clarity and calm